When analyzing economic data, we often encounter relationships that aren't perfectly linear. The first chart illustrates a common issue with a simple linear fit. It often fails to capture the underlying pattern, leading to what we call underfitting. The model is too rigid and misses critical turning points in the data. On the other end of the spectrum, high-degree polynomials, as shown in the middle chart, can be overly flexible. While they might appear to fit the sample data perfectly, they often capture random noise, resulting in overfitting. This erratic and unstable behavior, particularly at the edges of our data, is a well-known problem called Runge's phenomenon. Fractional polynomials offer a powerful alternative. As depicted in the third chart, they strike a crucial balance. They are flexible enough to model complex, nonlinear curves accurately, yet they are constrained to avoid the wild oscillations and instability seen in high-degree polynomials. This data-driven approach provides a more precise and reliable fit, allowing us to better understand the true economic relationships. When faced with modeling a relationship, we first need to determine the appropriate approach. Our decision framework begins by asking, is the relationship fundamentally linear? If the answer is yes, then standard ordinary least squares, or OLS, regression is generally the most suitable method. If the relationship is clearly nonlinear, our next step is to consider whether economic theory or prior knowledge dictates a specific functional form. For instance, if you expect a Cobb-Douglas production function, you would use nonlinear least squares. However, if theory doesn't provide such a specific shape, we then evaluate the nature of our data. If the data is discontinuous or exhibits sharp, non-smooth changes, then piecewise regression or splines are excellent choices to capture those abrupt shifts. But if the relationship is nonlinear, without a specific theoretical shape, and the data itself is continuous and smooth, then fractional polynomials, or FP, emerge as the ideal solution. FP offers a flexible, data-driven approach to discover the best curve without forcing a preconceived shape, striking a balance between rigidity and overfitting. Now that we see where fractional polynomials fit in, let's compare them directly to the conventional polynomials we're more familiar with. Today, we're directly comparing conventional polynomial regression with the fractional polynomial approach. On the left, you see conventional polynomials, which are limited to positive integer powers, like x, x squared, and so on. This restriction means they can only capture a narrow range of shapes, primarily parabolas and cubics, and are prone to unstable behavior at the data's edges, a problem known as Runge's phenomenon, often leading to overfitting. In contrast, fractional polynomials leverage a much richer and more flexible set of powers, as seen on the right with Stata's standard power set. This set includes negative values, fractions like negative 0.5 and 0.5, and crucially, a power of 0, which represents the natural logarithm of x. This expanded toolkit allows fractional polynomials to model a wider array of relationships, including important economic phenomena like reciprocals, roots, and asymptotic behavior, offering superior data-driven flexibility for complex curves. The general form of a fractional polynomial model is presented here. While it might look familiar, the crucial difference lies in how the powers, represented as P1 and P2, are determined. Unlike conventional polynomials that use sequential integer powers, these powers are not fixed in advance. Instead, they are selected from a predefined, restricted set of values. This set, typically used in software like Stata, includes not only integers, but also negative and fractional values, like -2, -1, -0.5, 0.5, and so on. A particularly important point is that a power of 0, as indicated, represents the natural logarithm of x, or ln of x. This logarithmic transformation is key for modeling relationships often seen in economics, such as diminishing returns. Furthermore, to maintain the model's flexibility and avoid issues if the selection process yields identical powers, a special rule applies. If P1 equals P2, the second term is multiplied by ln of x. Stata automatically searches this set to find the combination of powers that best fits your data. To effectively use fractional polynomials, there are a few important assumptions and prerequisites for your data. First, the variable being transformed, x, must be strictly positive. This is crucial because the power set includes operations like the natural logarithm and square root, which are undefined for 0 or negative values. If your data contains such values, you must shift it, for example, by adding a constant so the minimum value is greater than 0. Second, this method is specifically designed for continuous variables like age, GDP, or BMI. It is not appropriate for categorical or discrete data. Finally, while the curve we model is nonlinear, the fractional polynomial model itself maintains linearity in its parameters. This means we are transforming the variable x, not the coefficients, which allows the model to still be estimated using standard ordinary least squares, or OLS. For instance, if your income data includes 0 values, you'd need to create a new variable, say income shifted equals income plus 1, before applying the FP method. When working with fractional polynomials, we need a fundamental shift in how we interpret our results. Unlike standard linear regression, where a coefficient directly tells us the change in y for a one-unit change in x, this approach is invalid for fractional polynomials. The coefficients of the transformed variables, such as x to the -2 or x to the 0.5, do not possess a straightforward, economically meaningful interpretation. Attempting to interpret them directly would be misleading, as a one-unit change in a complex transformed term like age squared inverse simply isn't an intuitive concept. Instead, the correct way to understand the model is entirely through visualization. We must focus on the overall shape of the relationship that the model has uncovered. This means plotting the predicted values of y, or hat y, against your variable of interest to observe the curve and grasp the underlying economic relationship. In Stata, implementing fractional polynomials is straightforward using the FP prefix command. This command initiates the automated search for the best powers from the predefined set we discussed earlier. You specify the variable you want to transform within angle brackets, for example, h. These brackets are required to distinguish the variable being transformed from other covariants. The FP prefix can be used with a wide range of estimation commands, not just regress. This makes it a very versatile tool, allowing you to apply fractional polynomials to models for binary outcomes like logit, survival analysis with Stetcox, or generalized linear models with GLM, among many others. For instance, to model wages as a fractional polynomial of age while controlling for other factors, you'd type FP age, regress wage age, education, female. While this basic syntax works, there are two crucial options that you should almost always use to ensure your model is stable and interpretable, which we will cover next. Building on the basic FP syntax, there are two crucial options you should almost always use: scale and center. The scale option is vital for preventing numerical instability. Without it, raising large numbers, like a person's age to a power of 3, can generate extremely large values, leading to computational errors. Stata's scale option intelligently handles this by automatically rescaling the variable, dividing it by 10 or 100 before applying the fractional powers. This ensures numerical precision. Separately, the center option significantly improves the interpretability of your model's intercept. In many real-world scenarios, an x value of 0 is nonsensical. For instance, interpreting the intercept for wage at age 0 is meaningless. By using center, Stata shifts the variable by its mean, so your intercept then represents the predicted outcome at the average value of x. This makes the constant term economically meaningful. Together, specifying FP age, center scale, ensures your fractional polynomial models are both numerically robust and interpretable. Before we can run our fractional polynomial analysis, proper data preparation is crucial. We follow a simple 3-step checklist. First, always inspect your data thoroughly. Use a command like summarize age detail to check the range of your variable and, critically, to identify any zeros or negative values. This is essential because the fractional polynomial method, with its use of logarithms and square roots, requires the input variable to be strictly positive. Second, if you find any zeros or negative values, you must handle them. The most common and straightforward approach is to shift the variable by adding a constant, ensuring all values become strictly positive. For instance, you might create age shifted equals age plus 1. Finally, ensure the variable is properly set up for transformation. While advanced commands like fpgenerate or recode can be used for more complex scenarios, for most cases, simply having a strictly positive, continuous variable is sufficient. Once these steps are completed, your data will be ready for the fractional polynomial command. We're now moving into a practical application, using a classic economic scenario, modeling how wages evolve over a person's life cycle. This scatter plot illustrates hourly wage against age, drawn from our wagedata.dta dataset. It clearly shows a nonlinear relationship. We observe wages rising rapidly in early career stages, followed by a noticeable slowdown in growth, reaching a plateau, and potentially a slight decline in later working years. Our goal is to model this complex curve accurately. A conventional quadratic model would impose a symmetric parabolic shape, which, as we can visually infer, would not adequately capture the observed pattern, particularly the slower decline compared to the initial rapid rise. This is precisely where fractional polynomials become invaluable, allowing the data to determine the optimal, non-symmetric curve without forcing a preconceived shape. Let's now put everything into practice and run the fractional polynomial analysis in Stata. The command is fp age, center, scale, regress wage, age, education, female. Here, fp is the prefix for fractional polynomial analysis. Age specifies that the age variable should be transformed, and we include the essential center and scale options for numerical stability and meaningful interpretation. The core estimation is a regress command, with wage as our dependent variable and education and female as additional control variables. Once this command is executed, Stata automatically begins an extensive search. As you can see from the output, it fits a total of 44 different models, systematically testing various power combinations from our predefined set. This iterative process, indicated by the progress bar from 10% to 100%, aims to identify the model that best fits the data by minimizing its deviance. This table summarizes the exhaustive model search conducted by Stata. Its primary objective is to find the model with the lowest deviance, as a smaller deviance value signifies a superior fit to our data. The table systematically compares models of increasing complexity, starting with a simple linear model, then evaluating various single-power models, denoted as m equals 1, and finally, more complex two-power models, m equals 2. The p-values presented are crucial. They indicate whether moving to a more complex model offers a statistically significant improvement in fit. In our case, the significant p-value suggests that the two-power model, or m equals 2, provides a superior fit compared to its simpler counterparts. The final row for the best model, m equals 2, clearly identifies the optimal powers that Stata found, -2 and -0.5. These are the specific transformations that will be applied to our age variable in the final regression. After the automated selection process, Stata presents the final regression results, as you see here. The output now includes variables like age 1 and age 2. These are the new, transformed variables that Stata created based on the chosen fractional polynomial powers. Specifically, age 1 corresponds to age raised to the power of -0.5, and age 2 corresponds to age raised to the power of -2. It's crucial to remember that these are not simply age and age squared. As we've emphasized, you must not interpret the individual coefficients for age 1 and age 2 as simple slopes. Their values reflect the complex transformations and do not hold a direct intuitive economic meaning on their own. The true interpretation and understanding of this model's findings come from visualizing the combined effect of these transformed variables, which we will do next. This graph represents the culmination of our analysis, plotting the predicted wage against age based on our fractional polynomial model, with other variables held at their mean. This curve provides a clear visual representation of the complex relationship we've uncovered. The visualization reveals a compelling economic story: rapid wage growth during the early career, followed by a mid-career plateau where wage increases slow considerably, and then late career stability. This nuanced pattern, showing faster growth in early years, especially between 20 and 35, and then a flattening after age 45, is a classic finding in labor economics. Such insights would be missed by a simple linear model or misrepresented by a rigid quadratic one. The fractional polynomial has truly allowed the data to tell its own rich story. In Stata, you can easily generate this plot using post-estimation commands like fpplot or by utilizing the margins and marginsplot commands. After fitting any regression model, including fractional polynomials, it's crucial to perform post-estimation diagnostics to assess its validity. The first plot, residuals versus fitted, is vital for checking the assumption of homoscedasticity. Ideally, we want to see the residuals randomly scattered around 0, indicating constant variance. In our example, we observe the variance might slightly increase with age, suggesting potential heteroscedasticity, which might warrant using robust standard errors. The second plot, the partial residual plot, helps us evaluate the goodness of fit specifically for the nonlinear curve we've estimated. It plots the part of the outcome explained by the variable of interest against that variable. If the model accurately captures the underlying relationship, the data points in this plot should align well with our fitted curve, confirming the fractional polynomial's ability to represent the complex age-wage relationship. To summarize, there are 3 key takeaways from our discussion on fractional polynomials. First, remember the principle of flexibility. Fractional polynomials provide a superior fit to the data by adapting to complex nonlinear shapes, outperforming the rigid constraints of conventional polynomials. Second, appreciate the power of automation. Stata's fp command significantly simplifies the process by automatically selecting the optimal powers, making this advanced technique remarkably user-friendly. Finally, and most critically, prioritize visualization. The true economic interpretation of an FP model comes from plotting the fitted curve, not from dissecting coefficients in a table. Always visualize your results to understand the underlying relationship. For further reading, I highly recommend the seminal work by Royston and Altman, the detailed Stata manual entry for the FP command, and Mitchell's insightful book on interpreting and visualizing regression models with Stata.